welcome you to the lecture 6 on fluid mechanics 2. As in the last class we discussed about fluid statics, that means fluid at the rest, and again I want to repeat it that I have been following these 3 reference books. One is Sinjal Simbala, Fluid Mechanics Fundamentals and the Applications. Then very concise book on Frankman White, that is a fluid mechanics, and the fluid mechanics by Vidyasagar Pani. Now let us go to the next levels. We will discuss today the concept of the buoyancy, very well known Archimedes principles. In that we will also discuss it the metacenters or metacentric height, how to determine the metacentric height of a floating object, and we also will talk about the stability of the floating object, and then we will talk about if there is a rigid body motions, the liquids in a rigid body motions, what could be the pressure diagrams, and also we will discuss is that rigid body motions when you have a uniform angular rotations. With this, let me start the lectures today. Before starting these lectures, let us see these over slides. This is what is showing that how the fluid mechanics has changed our life. If you look at this arrow, which is maybe very ancient times, first the human civilization starting the hunting. Hunting is a main occupation for the life. That is what having a top speed of 321 kilometer per hour and as equivalent to Mach number of 0.3. So, the art or knowledge of aerodynamics of what I want to say is that this the arrow or the aerodynamics of the arrows, that is what was known to very ancient people, that is what they use for hunting, and the design of the arrows as changes as revolves with the time, that different type of the speed, different type of velocity, different type of range, that is what is designed, and most of these designs what is done it from the experience. But what it happened maybe last 1 century, we have developed fighter planes, and that is what if you can look at the figures like the CH-47F Chincoid with the top speed is 315 kilometer per hours, which will have a Mach number of 0.3. So, if you look at the arrangement of this the aircraft, also you can see this arrangement of the aircraft and their wings to create a vortex, and because of creating the vortex, that what will be difference the pressures, and that what will be resulting a off-fleet force, and the drag and the off-fleet force, that what will keep it to different vehicle, this, the defense vehicles, which is having a Mach numbers of 0.39, and it can go up to altitudes of 6,000 meters, and top speed is 411 kilometer per hour. The similar way, if you look at the newer flights, what the space fighter planes are available, like the F-16s, Rafales, or the Blackbirds. If you look at their speeds, 2000 kilometer per hour, and their Mach numbers is more than 2, and basically this Blackbird who is having the top speed is goes up to 3660 kilometer per hour, and these altitudes can go up to 26,000. How this technology is developed so fastly to go to a Blackbird level because of the knowledge of fluid mechanics, not only the analytical fluid mechanics, but also it's developed in terms of numerical methods, the computational fluid dynamics, as well as the full scale the wind tunnel facility. The most of these advanced fighter planes are tested in full scale wind tunnel facilities. So that's what my point to say it. If you look at the knowledge of the fluid mechanics can help us to design fighter aircraft which can go as fast as 3,600 kilometer per hours with a altitudes of 26,000 and which is the Mach numbers 3.35. So, this what it is a possible because of the knowledge of the fluid mechanics. So, because of the extensive experiment conducting in full scale wind tunnels, series of numerical testing conducting for this type of the aircraft, it is now the possible to develop this type of aircraft and not having any failure of this type of things. So, what I am to emphasize that the fluid mechanics knowledge is not limited to a textbook of solving few academic problems, but we should have a more knowledge. We should understand the fluid mechanics process more details as we are developing our fluid mechanics which are there more analytical way. Now, the full scale wind tunnel facilities, the numerical methods, CFD, advancement of CFD made us to look the fluid mechanics in different way. So, that is what my objective to say that fluid mechanics is now is a integral part to develop our the aircraft systems what I have just given you the examples. Let us come back to the topics what we have been discussing that fluid at the rest. Okay. As I told it when the fluid at the rest we have the two force component. One is force due to the pressures and the second is the gravity force. There is no velocity components, there is no shear stress component. So, that is the reasons if you take a control volumes, it is easy to draw the pressure diagrams and from that pressure diagrams, if you equate with the gravity force, you can solve the problems. That is a very basic concept what we have used in fluid at the rest. So, now if you look it, if we have a to determine what could be the forces on a curved surface, what the problems we face it. If you have a, let me take these examples, you have the free surface and you have a curved surface and you have the liquid which is having the density let be the rho, density is let be the rho. If it is that conditions, what is the basic difference of this point is here that if you take any point as you know it, the pressure is a scalar quantity and we will have the pressure component will be normal to the point where you are considering the surface. In that case, what it happens when you have a curved surface, the directions of the pressure that what changes from the point to point. So, because of that we have to resolve this force component in 3 Cartesian coordinate x, y, z. Then we can take a small element, do the integrations over the surface because you know the pressure diagrams. Then we can integrate it to solve, get it what could be the force because of these pressures and the weight of the fluid. That what can be done it. The problems comes is that we can simplify that ones, like we can resolve the in a curved surface into a two part horizontal and vertical components. Okay. So, like here what the diagrams have shown it, it is a curved surfaces and that is a projected surface on the verticals and on that the horizontal force is acting it and verticals are working in the downward directions. If it is that the component, if I draw the free body diagrams, it will come like this. That means there will be the free surface here and the top of the free surface there will be weight due to the air. Then there will be weight above this curved surface W1 and W2, that is a weight of the liquid what is we have. Now, if I draw this is my control volume and the pressure diagrams. Okay. This is what my control volume and if I draw the pressure diagrams, I can draw the pressure diagrams which will be the triangular shape, the linearly will increases as z we go further down and down. So, that way we will have the pressure diagram like this. So, you can see that if you look at the point above the CB, the same pressure diagram in the both the side which is representing force F1, F1 here. That means these two forces will be cancelled out when we take this total pressure diagram to find out what could be the force due to these pressures. So, F1, F2 will be cancelled out, only you will have the pressure component which will be the trapezoidal pressure component from this C point to this point. So, in horizontal directions we will have the pressure, that is what only the pressure diagrams will trans over this curved surface will be a trapezoidal shape. So, if this is the pressure diagrams, you know from the height we can determine what is the pressure at the C, what is the pressure at this point. If I know it, the area of these triangles will show us what will be the force Fh is acting over that, multiply with the area, we can get it what will be the pressure force is acting in the horizontal direction. In vertical direction, if you see this diagrams, the basically the weight of the fluid liquid what will become as a vertical component. That is what will be the W1, W2 and WR. That will be the FP will be the balanced by the weight of the liquid what we have, and WR can be neglected as compared to the W1 and W2. So, it is very easy to component the vertical component pressure on curve equal to magnitude and direction of weight of the entire column on fluid, both liquid and aqueous surface above the curved surface. That is what we said that. And what will be the horizontal force component? That what will be force on the plane area, that what is a projection of the curved surface onto a vertical plane normal to this component. That what either through the pressure diagrams you can compute the force in the horizontal directions, or you get it what could be the projected area on this the vertical plane and find out its centroid locations. At that central location, if you know the pressures, multiply with area, that what will be give you the force component. Then you know the line of action of the force where it is acting it for the weight part, the vertical component as well as horizontal component. If you know these two force component in vertical and horizontal direction and their line of actions, you can easily using the vector calculus algebra you can compute what will be the resultant forces and where is the line of actions of resultant forces. So, we will solve some numerical problems to demonstrate that, but very basic idea is that whenever you have a curved surface, you draw a pressure diagrams, consider a control volume, draw the pressure diagrams, then equate the force component in horizontal directions and the vertical direction, and those force component you find out from the pressure diagram and the weight of the liquids. Now, let us come into very interesting topics what is used in buoyancy. As you know it, the famous scientist Archimedes what invented this buoyancy concept when he was in a bathtub, experienced the lighter weight because of the buoyancy forces. So, what is the buoyancy force? If you know it, that it is a very simple things that whenever you have any object submerged within a liquid, what will happen it that there will be a force from the top, also force from the bottom. There will be force from the top because of this the liquid mass, the top of the liquid mass, that force vertical force will come it, and there will be force will be upward direction. How much that will come it? If you look at that, if take a control volumes like this, you have the surface where P1 pressure is coming at the top, the P2 pressure is coming to here, and the distance between that these 2 points, if you define Z1 by Z2, then you can find out pressure at the P2 is a is equal to the height and the rho g. Similar way, the pressure at this point rho g and the height from the free surface. So, if you subtract the pressure multiplied with the delta L, you can find out it will be the force component what will come it, which is a equivalent to weight of this element as equivalent to weight of liquid displayed by that control volume. That means, this control volume what you have chosen it, if you consider of submerged body, that is as equivalent to the liquid, that is what display the water liquid for because of this submergence of this object, that what will be the vertical force what will you get it, what will be experience it. So, we will have a weight of the fluid, that is what is the unit weight and the volumes. The unit weight and the volume, that is what is surface area and the vertical height difference what we have. If you look at this total upward buoyant forces, if I have taken the element, if I do the integrations, finally we will get it unit weight of the liquid where we submerged the body and the volume of the body, that is what will be the buoyant force and what acts in upward directions. So, that is what is a total upward buoyant force, that what it works. Now, if you look at another point is also look at that the center of buoyancy, that means the line of actions of the buoyant force, like we try to compute for the other force component. So, line of actions of the buoyant force is a center of buoyancy, that means at which point the buoyancy force acts, that is what the center of buoyancy, that is what is necessary to counter with a gravity weight of the floating object. Like for example, if you look at very interesting photographs what we have shown it here a swimmer, okay, you can see that the CG where the weight of the body is there, okay, the center gravity points and the CG weight of the body, and the whatever the liquid displayed by this swimmer, that what having a point here the center of buoyancy, and at that center the buoyant force is working like this. If you looking this figure, you can say that there will be torque or moment will be because of this force imbalance. Okay. So, that is the reasons if you look at any swimmers, they try to do some swimming activities to remain as a floating conditions, because these the center of buoyancy and the CG, they do not lie in the same locations. Because of that, there will be a torque will be there, and that torque to balance it, any swimmer if you look it to remain it floating conditions does slight bit swimming activities, the change the flow pattern such a way that the additional force he can generate it to counterbalance this moment. So, very interesting studies like this, if you look at that, the basically the center of buoyancy, if you look at that should be a center of displayed volume of the fluids. So, that is what to summarize and to make it very easy to say that the Archimedes principles what it says that a body immersed in a fluid experience a vertical buoyant force. That means, whenever you immerse a body in a fluid, you will have a vertical buoyant force will be acted, which will be equal to weight of the fluid displayed by the body, and the buoyant force act upward through the centroid of the displaced volume, which we discuss it. Same thing is written in very concise way. That is what the Archimedes principles. Okay. So, is way back in 2 or 3 BC. Okay, that is the knowledge of the fluid mechanics as old as just starting of the civilizations. So, if you look at that way, so we can say that the floating body displays the one weight. In case of the floating body, what will happen? It is that it can totally submerged in the floating body. The floating body case, the weight of the object is counterbalanced by the buoyant force. So, that what is happening? The buoyant force is a counterbalanced by the weight of weight of the object. So, that is what it happens, it the floating and the body weight, that what both will counterbalance it. But some of the case you can have a layered fluid, that means you can have a different type of the fluids will be there with a different distance density like rho 1, rho 2, rho 3, and if you have a object is floating an interface between two density. So, same concept we can consider it, but you have to consider the pressure diagrams, you can find out which part of the volume displayed by which liquid, and based on that you can have understand the problems will be the different as compared to single liquid concept where the rho a single rho value is there. That is what is quite easier as compared to the layered fluids. Now, let us discuss about stability of floating object, stability of floating objects like the ship. How much stability we have a floating objects. Now, let us understand the principles, how the concept is comes in. As we discuss that there will be a gravity force which will act the CG of the floating object, and there will be the force which is a buoyant force will be act at the CG of the displaced liquid, that what will be the center of buoyancy. So, these two force components act at two different locations. One is a CG of floating object, another is a CG of the displaced volume of the fluid. Because of that, we will have the stability problems, that if I just do a small disturbance or just slightly rotate the a floating object, then what it happens, it does that come back to original positions. If it is come back to original conditions, then I will tell it, it is a stable, it has a stabilities, it can come back, any small change will not change the stability of the floating object, it will come back to original positions. But other way and others, if I talk about unstable equilibriums, that means if there is a slight bit change, slight bit tilting the floating objects, and that what generate a large rocks and finally capsized, then we will tell it is the unstable equilibriums. So, let me discuss about these three equilibrium concepts: natural equilibriums, stable equilibriums, and unstable equilibriums. So, you can understand it if somebody wants to design a ship, he has to find out the ship should have stable equilibrium conditions. So, any point of the ship that should be follow a stable equilibrium, any disturbances done in that should not capsize, they cannot have an overturning movement to capsize that. Instead of that, it can come to a stable locations, comes to the stable locations. So, that is the reasons there are a lot of detailed studies there in the people who are design the ships, but here we will talk about very basic things, that how we can find out the stability of a floating object, and the stable in a three ways we define: natural equilibrium, stable equilibrium, and unstable equilibrium. Before doing that, let me introduce one point which is we call the meta centers. Okay, that is what is called the meta center. What is that meta centers? Okay. If I tilt a floating object to a angle of delta theta, then there will be new water lines will come in. That means the shape will change it, like the, for example, for this case the will tilting this part. So, new water lines will come it. As because of that, the buoyancy, the center of buoyancy will change it from B to B dash. It will change from B to B dash, and along that we will have the buoyancy force what is going to act it. The center of buoyancy will change from B to B dash, and along that locations we will have the buoyancy force will be acted. If a very simple case, which is theoretical case, it does not happen in real ship design case, because if there is a conditions that the buoyancy force and the weight, they are acting at the same points, the buoyancy force, and if I extend the buoyancy force, that what this line of the buoyancy force is coincide with the CG of the floating object where the weight is acting it, then that is the point we call metacenters. That means a vertical line drawn upward by B intersect the line of symmetry at a point which M is defined as a metacentric, which is a independent theta angle for the small changes. So, if a conditions what you have that M is coincides with the G, that is what I say, that very rare conditions happens that the M and the G will be the same point, the metacenters and the center of gravity in the same point, then we call natural equilibriums. Okay. That means if you tilt it that again this what will be remain in that shape. Okay. That what will be the natural equilibrium conditions. Okay. But many of the cases what it happens is like this, called a stable equilibrium. Like we tilted this floating object, as we tilted this floating object, the B is shifted to B dash. The center of buoyancy is shifted from B dash. As the water line changes, the displaced water liquid, that what is changes, and their center of buoyancy changes from B to B dash, and FB, the buoyant force does not change much, does not change it, because the same volume of liquid displayed by this object, only the center of buoyancy changes from the B to B dash. Because of that, if you find out the metacentric point, which is a M here, and G is the CG point. So, in this case we have the BM is greater than BG, BM is greater than BG. That means the M is the lies above of the G points. At that time, if you look it, there will be a restoring movement will be generated. There will be a restoring movement will be generated to bring this the tilted or object to the right position, the initial positions. That's the reasons restoring couple of movement will happen it, that will bring back this floating object with a minor tilting, again it can come back it. So, since this is the process happens where BM is greater than BG, and we call it stable equilibrium, we call stable equilibrium. That means this type of ships or any floating object, if you do a minor instability or minor angular movement, after certain times you will see that it again coming back to the initial conditions. So, that type of floating object we call it is at stable equilibrium. Other way around, if you have a BM less than BG, same concept. Okay. Now, B has changed to B dash, the center of buoyancy has changed it, but the M lies in between B and G. But if you look at the moment, what generate because of this, the weight and the FV will be the overturning moment. Because of that, this floating body will be capsized, it will be capsized. So, in that case, the theoretically BM, the distance between the buoyancy and the metacentric height, metacenters, that BM will be lesser than the BG, and we have a unstable equilibrium. So, let me summarize that when you have a floating object, to test its stability, we generate a small disturbance of tilted with a small angle delta theta, and find out because of that how the center of buoyancy changes it. And that is the line of actions of the buoyancy force of new locations, the meet with the vertical axis, that is the location is called the metacenter. That's the location of the metacenter with respect to the CG and the earlier buoyant centers, that what will decide it whether it is a natural equilibrium, stable equilibrium or unstable equilibrium. The theoretically, if you have BM, BG having a relationship like its BM is greater than BG, BM is less than BG, you have a stable or unstable equilibrium. Now, how to compute this, the metacentric height? Let you have a floating object like this, okay, and you consider the unit width of this one, which is a perpendicular to this surface, that is what unit width is there. So, what we will do it? Let have a the initial positions of water lines goes through this C to D. So, initially it was C to D and it was tilted. Okay. Because of the tilting, as explained earlier, the B changes to B1 dash, B changes to B1 dash. Okay. The basic idea is to find out how we can establish a relationship between the metacentric height. Okay. So, if you look at that, the center of buoyancy changes from B to B dash, that is what is x bar distance from this. Okay. And because of that, what it happens is this area will be exposed out of the liquid, this is the area come into the liquid surface. Now, we want to compute it, what will be the x bar, that what we can do in very simple way, that we can take it, the area of the moment of inertia of water line can be about axis of tilting, about the axis of tilting, that means y, if I take it the force into distance, that what is the moment. But here I am just giving the volume, because the force will be the rho g and the volume. What will be the force? The weight of the fluid, that what will be the rho g into volume. Since the rho g is a constant, so we use just the volume expressions here to equate the moment, nothing else. That is what you have to understand. It is just taking a moment of the force, that is what it act because of this fluid displacement. If you look at the first, the moment of this part, volume what we have considered A, O, B, D, E, that means this part. Okay. That is what will be the 3 component will be there, because of this component will be the minus, this component will be positive. That is what is happened. C, O, B, D will be the positive and this way. Since this is the axis of symmetry, these values becomes 0. So, you have a just the volume moment what we have considered, the force moment what we have considered for the OBD and COA. Now, we can result what is L. The L will be the what will be the dA? You take a small element, dA will be the x tan theta dx, x tan theta dx. If you take a tan theta common out of that, that means this is what is showing that along this water line, the dA area, the x square 1, that was the moment of inertia along the axis passing through the symmetrical axis, that what into the tan theta. So, this is what is establish a relationship between x bar, the volume of liquid, inertia passing through the O point, and the tan theta, theta is a angle of tilting. So, if we use that from the simple geometry, you can find that mb dash will be x bar by tan theta. Okay. If you have a look at these triangles, we can find out that this is what by this definition I naught by V sum mod, the mb will be the mg plus gb, so finally the mg will be this component minus gb. So, any object we can find out the center of gravity, we can find out the center of buoyancy, that what can be computed. We can find the V submerged, you can get it I naught, then we can compute the mg. If mg is positive, then it is stable equilibriums. Okay. If is mg equal to 0, then we can say is a natural equilibriums. Okay. If its mg is negative, then we call unstable equilibrium conditions. So, with this we compute it that what will be the mg of a floating object. Just let you see this, just want to say that what are the applications of the floating stability of the floating objects. Okay. And if you look at that, if you can see observe of a dead piece, you can see that it is what tilted in when a piece is dead conditions. So, finally, you have to see that it is floating at the side unstable, waving flat sides off. This because of the change of the center of buoyancy, and when the piece is swimming, is the symmetric axis are the different, and once it is dead, that what it changes it cannot be stability position of that. And many of the interesting photographs or the video you can see it that the melting of icebergs or falling of the icebergs. Okay, very beautiful scenic beauties has come it, but when these icebergs are following it, we do not know it what it happens in underground of these big icebergs, giant icebergs. For examples, because of the heating system of the oceans, there could be underwater melting. So, at the surface could be iceberg is standing it, but below, because of the heating systems of the undercurrent, the heating systems of the oceans, there could be a melting which is going down below of a iceberg. As this melting it, you see that at a certain points it will come its center buoyancy will change it, and the point of mg what we have discussing is that becomes a negatives, and it can immediately collapse it. So, that what is a very, there is sudden collapse of a big iceberg happens it, which because of the presence of the underwater melting of the system. If I take a simple the specific gravity of the ice and the specific gravity of sea waters, any iceberg, if you look at that, the 1/8% of the icebergs will be floating condition on the surface. The 7/8% will be the inside the sea. So, only with what you see this 1/8% of the icebergs what we see it. The 7/8% of the iceberg inside comes in that, and we do not know what could be the shape of that iceberg. Okay. So, that is the reason if you know it, if you can see the great movie of Titanic, which is stuck in because of stuck with the iceberg in 1912, because of not underestimating, not knowing, having the knowledge of the iceberg. That is what the point is, because we look it from the top, there iceberg of 1/8, 7/8% of iceberg is within the waters. So, 1912 you can know it, there was not much technology to do at present what we have, like the space technology, the GPS technology, the radar technology. We can do detailed sounding what type of the iceberg is there, what is the extent of the icebergs. We have a satellite remote sensing to monitor the icebergs, but that is what was not there. Even if you look at the Titanic movie, which is one of the largest ship in that periods, it was very, very expensive interior decorations, but they did not understand the technology is necessary for to make a safety of the big Titanic ship. That is what it happened. So, that is what the tragedy come it. So, what my point is to say that, so as a engineer we may be build a big interior design expensive ship, but also we should look at the safety of the ship, or other way around, we should always have a knowledge of the fluid mechanics, which gives us a lot of the safeties, like when you are constructing a big towers, big high rise buildings, the safety is more important as compared to have a big interior, very expensive interior designs. Okay. With this, what I am to say that the stability of floating objects, what is we are talking about, it has lot of examples of the stability of the floating objects. Naturally you can see it, and that is what revitalize the navigation systems in the oceans. It has now brought its new technology, new way to do this safer navigations as compared to the 1912s, but that what is a lesson learned for engineers, that instead of looking the making a bigger ship, the best, the beautiful interior, but the safety is the first. That is what my point to tell you. Okay, so let us look at simple experiment, metacentric height experimental setups, which just balancing the weight, we can measure the metacentric height of a floating object like this, and this type of facilities are there. Any fluid mechanics lab, you can just measure the metacentric height and find out the stability of floating object. Now let us come to the another component on fluid statics, then that means fluid at the rest, but we are looking at a rigid body motions. That means what it happens, that if I have a half filled liquid containers, that means I have a half filled liquid containers, it has a free surface and this is the what the containers. If I accelerate it with the accelerations A, okay, I have a tank and I am just accelerating with the accelerations A. So, you can imagine it, what will happen? The fluid will slosh it, that means fluid will be having a sloshing, its up and down effects. But after certain times, what will come it, that will be new free surface will be created, sloshing will stop it, new free surface will come it, and that what will move it, that acceleration A. So, when it comes to a stage there is no sloshing, the new free surface is created and the fluid now behave as if a rigid body. That means there is no velocity gradient, no shear strain rate, no shear stress formations. So, it acts like a rigid body motions, moving with accelerations A. So, it is a very simplified case that if you have a container, you have a tank containing the liquid which is a half filled and it is moving with a constant accelerations. After certain times, you can see that it will make a different free surface, it will change the liquid will have a different the free surface, and after that there will be no change of the velocity gradients and no shear stress strain formation or the shear stress formation. So, because of that the problem is now it is quite simplified and it becomes a just as if a rigid body motions. That means the liquid is there, but we can consider because there is no shear stress, only this have. That means what are the force components are there? The force components are, one is force due to the pressures, gravity force and force due to this accelerations component. So, this we have the three force components now. Okay. There is no shear stress, so there is no viscous components are there. So, only we have the three force component, as I derived earlier, that we have grade P is equal to rho g. G is here the vector quantity, g is a vector quantity, Now, if I have a acceleration is vector quantity, then you can simply consider the control volumes is moving with a accelerations a, you find out the relative accelerations to equate with the pressure gradients. So, this is a vector equations defining for a control volumes which is moving with constant accelerations of a, and we are equating with pressure, gravity and particle accelerations or the control volume accelerations what we have. Now, if you look at these interesting equations which is a simplified equations what we got it for these the liquid containers, that you can see that the change of the pressure gradient and G minus A the pressure gradient acts in the direction of G minus A. That means the line of constant pressures are perpendicular to this direction. So, if you know this acceleration due to gravity vectors, you know the acceleration vectors, the vectorically difference between these two, that directions will give us the line of constant pressures will be the perpendicular to that direction. That means the free surface will tilt at it, the pressure diagrams will change which will be perpendicular to that. Now, if you look at, if I draw the vectorically the components, that this the object is moving like having the accelerations a, moving as a acceleration a is a vectorical component, it can have the scalar component in 3 x, y, z coordinate systems. So, if I just balancing this part as the vectorical additions, if I do it, and because of that you can see the constant pressure diagrams will have a tilting with a theta which is balancing with the force component. Tan theta will be balancing the force component because of Ax, the acceleration, the scalar quantity in x direction, the acceleration z directions component of the scalar quantity, and g, if the tan theta just the vectorically in this part, that part will be the tan theta on this. So, what it indicates now, the surface will be tilted with a theta degree and will make a constant pressure diagram. That means, if you have the free surface, that means the free surface will be tilted with a theta degree such a way that these two force component will counterbalance by the force due to the pressure gradient. That is the very vectorically we are computing it. So, the pressure will be changed like this. So, your free surface atmospheric pressure lines also we can draw it, as I given the examples like this, we will have the tilting surface as we have a accelerations of this, and that tilting surface the angle it depends upon the acceleration component in x directions and the z direction and g value to find out what will be the theta component. That way we can vectorically solve these problems, and that is what is the explanations, that the surface of the constant pressure must be perpendicular to the pressure gradient and it will be tilted downward such a way that theta is this part x a z. Okay. It will be z here. So, tan theta in the same diagrams. So, if you have the free surface also will be tilted, as I explained it, the free surface also constant pressure diagrams, free surface will be the tilted on that way to get it. But if you do not have the enough the wall length, the wall height, sometimes liquid can spill away from this because of, like for example, you have the containers are moving with a particular acceleration, again you increase the accelerations further and further. Okay. It will come at such a stage that it may overflow from the liquid from the tank, open tank if you have. If you have a pressurized conditions, we can solve it, a problem like that when I will solve the numerical problems. So, the basically what you can try to know it, that as we move with the constant accelerations, the free surface changes, the pressure diagram changes it, and that what equate with two force component. One is particle accelerations component, another is the gravity force component. With a simple hydrostatic equations, we can write it. And similar way, the rate of increasing the pressure in the directions of pressure gradient will be the greater than the ordinary pressure statics, which is definitely true now, which will be the d pi by dx. The rho g is the resultant component of Ax and Ag, vector-related component what will go it, which will be the perpendicular to this will be the rho g. You can compute it, what will be the conditions. Now, let these conditions consider similar way of the rigid body rotations. Okay. Now, we are talking about the rotations. If you look at any chemical industry, the dairy industry, many times we do the mixing of the two liquids. What we do it, we actually do the uniform rotations of the liquid containers. Okay. So, if you do a uniform rotations of liquid containers, so you can understand it that if I have the liquid filled with these ones and I start the rotating of these ones. So, definitely you can, after certain times, it will have a shape like this. So, when it comes to a constant the shape, since these are uniform rotations along we are doing it, there will be the same conditions, the velocity gradient will not be there, no shear strain rate, also shear stress. So, it is again as if like a rigid body motions, that means a ball is rotating with a uniform rotations. It has a two components, one is the centripetal forces, another is the gravity forces. That what will equate it. But in this case, we are talking in terms of cylindrical coordinate systems. Vectorically, we are representing it. That's the reasons you just look at because this is a quite general problem. Any type of rotations, we can solve it, considering the cylindrical coordinate systems like k and the IR, the unit vector along the radius, we will have a r and j, and we have a uniform rotations we are doing it, and because of that you can understand it, the centripetal accelerations will be this part. Okay. Here it is a representing as a vector notations. Okay. What is the position vectors, angular velocity, that the centripetal accelerations what will become it, you can, as you know it, the minus rho omega square IR, that what will come it. Now, this component will be balanced by the pressure gradient component. Pressure gradient component rho g minus A. A, we know it, the centripetal accelerations component what you have got it, and if you put it the proper sign conventions, you will get it, grad phi is rho g k, and the centripetal acceleration component in the radial unit vector directions, the force acting in the negative of the gravity force is acting the negative of z directions, that what balance with the delta p. So, if you look at that, if you have a constant translations, accelerations or uniform rotations, the gradient of p is equal to rho times of the vectorical difference between acceleration due to gravity and the acceleration. In case of uniform rotations, we are using the centripetal acceleration component, that is rho omega square IR. And here we represent in terms of vectors, that is the reasons IR is a unit vector in radial directions and the k is the unit vector in the z direction. So, as the vector components we have put it, then finally we get a equations, this equation need to be solved to determine what will be the pressure. Now, let us show it the solving this part. We can solve this one pressure field considering two equations component wise. Okay. One is a z component, another is IR component. So, you can integrate this separately and substitute the boundary conditions to get what will be general equation form. So, first integrations will come with this, with a constant of integrations will be fz. The second integrations will come with this, which is partial differential equation in z direction. P is a function of z and the r. So, finally, if you use these two terms with an additional constant, the pressure will follow like this. Okay. Then you substitute the boundary conditions, that you keep it your origin such a way that the pressure let be P naught at that locations. The origins of your coordinate axis where you have a pressure is P naught, then this constant becomes a P naught. Okay. Then you will have the pressure equations like this, or if you just rearrange it, you will get this part, which will be a parabolic equation format. That means, as we already discussed, is that when you rotate uniformly, your free surface will follow a paraboloid shape, will follow a paraboloid force. As the free surface follow the paraboloid, that all the pressure diagrams also will follow the similar way. P2, P3, P4 will follow that. For a simplified case, because this is very general case, if you take a cylinder, which is very simplified case, okay, it's a radius r having a uniform radius of that, then you can find out these parabolic shapes, and from the basic concept of parabola, you can find out the volume, you can find out that the half of water will be displayed from the surface, the initial conditions to the top, and you can find what will be the height. So, which is very easy, because in case of cylindrical with a radius r, we can simplify these general problems and you can get it a direct equations to compute these ones. But the real life problems, when you have oil tank in a rocket which moves with the rotation component will be the vectorial component. It is not a cylinders are rotating in a like a chemical or a dairy industry where everything is fixed. So, it can be rotated only, we can consider a simple cylindrical case and solve the problems. But real life problems, like there is a fuel tank in a rocket and the rocket is moving with different accelerations field at different field, what could be the fuel tank pressure diagrams, and what could be the conditions of the fuel tank when the pressure what will be exerted because of these, those need to be studied. That's the reasons look it in a vectorial form to solve these problems, where we just have to remember it, the gradient of pressures is equal to the density times of the vectorial difference between acceleration due to gravity and the centripetal accelerations component because of uniform rotations. Then you solve these problems, which can be done it for any problem, any shape of container, as compared to the simplified case like cylindrical containers rotating with is center of axis, which is a very simplified case. That can be also used for, as I said, that where we know the rotations, we know the cylinders, and we rotate with a uniform rotations for mixing of the liquids. That can be used as simple formulas, but in case of real life problems or the rocket, fuel tank in rocket, we have to look at vectorial forms. You can see this type of post vortex experimental setups, which with having a motor arrangement to make a uniform rotations, then to measure the shape of the free surface with a gauging systems. With the different rotations, you can have a different free surface, and you can compare with the theoretical value whether what you are getting from experimental do they match each other. If not, then you find out why it is not. Definitely, if you can understand it, what we get is a theoretical case like having a uniform rotations, the free surface what you get it for a cylinder case, that may not come it in experimentally, because in case of the experimental we have a lot of uncertainty in the measurement, the making uniform iterations perfectly, that also not possible. So, you try to understand it, there will be a difference between the experiments as well as the theoretical consider, because that was does not have any uncertainty in a measurement, in any uncertainty in the experimental system, that what is considered as a uniform rotations, theoretically it is possible, then what it happens it, but that the condition to do in an experiment, it is not that easy. That is the reason there will be a difference between the experimental profile and the theoretical profile. Now, let me summarize today's lectures that we introduce a center of buoyancy concept, we discuss about 2 or 3 basic concept of Archimedes, which is very simple concept of that. We discuss of the metacentric height, and also we talk about you as you have to remember of metacentric height in terms of metacenters lies below or above, or mg's coincides each other. We have a different conditions like stable, unstables, or the natural conditions, and we discuss about the rigid body motions, uniform linear accelerations, rigid body motions, the pressure diagrams. I can again tell about you Archimedes principle still hold good, okay, even if we are in 21st centuries, that a body immersed in the fluid experience a vertical buoyant forces equal to the weight of the fluid displayed by the body. This process makes lot of the process from micro level to macro levels. All this natural process, what it happens from micro water vapor to big water global circulations patterns, the buoyancy force also work it. So, we make with giving a lot of respects to these Archimedes principles, which help us to understand very complex process with this buoyant force concept as well as the center of buoyancy, metacentric height. Thank you lot.